you ever look at a Formula One car or a modern jetliner and just wonder, how is that thing so light, but also so unbelievably strong? Well, the answer is in these amazing advanced materials called composites. And today, here on Next Gen Manufacturing, we are going deep inside the lab to uncover the really clever science they use to test these super materials that are quite literally building our future. So here's our game plan. We're going to start with what these materials actually are, and then we'll get into the big puzzle they create for engineers. From there, we'll check out the super elegant solution, a vibration test, see how it works, learn how to crack the code on the results, and then tie it all back to why next-gen manufacturing is so strong. Let's get right to it. So, what is the secret ingredient that's powering so much of our modern tech? To put it simply, a composite is basically a team-up of two or more materials, and when they're combined, they create something new that has way better properties than the individual parts. A classic example is carbon fiber reinforced polymer. You've got these tiny, super strong carbon fibers swimming in a plastic matrix. The result? A material that's lighter than aluminum but actually stronger than steel. But as you can imagine, this combination also creates a really unique challenge for the engineers who have to test its limits. And that brings us to the central mystery that engineers are up against. You can think of this as the case file for our investigation today. Why are composites so darn difficult to really understand and test? Okay, the number one clue is a property with a big, fancy name, anisotropy. It's a bit of a mouthful, I know, but the idea behind it is actually super intuitive. All it means is that the material's properties, like its strength or how stiff it is, are different depending on which direction you measure them. Here's an easy way to think about it. A block of aluminum is what we call isotropic. It has the same strength no matter which way you pull on it. Up, down, sideways, it doesn't care. A composite, though, is anisotropic. It acts a lot more like a piece of wood. You know how wood is really strong along the grain, but it's super easy to split it across the grain? That's it. That's anisotropy. And this directional strength is a huge advantage, but it makes testing incredibly complicated. So, you've got this triple threat of challenges engineers are juggling. First, as we just saw, there's anisotropy. Second is something called heterogeneous. That's just the fact that it's made of different things, like fibers and a resin, which all behave differently. And third, the actual shape of the parts. You can't just slice a nice flat test piece out of the curved wing of an airplane, right? It just doesn't work that way. So how in the world do scientists solve this puzzle? Well, instead of doing the obvious thing, like pulling a material apart until it breaks, they use a much more elegant, non-destructive method to kind of listen to its secrets. And this is the key question, isn't it? If you have to destroy a sample to test it, you obviously can't use the actual part you want to build. So you need a clever way to interrogate the material, to ask it, hey, how strong are you, without doing any damage? And the answer is pretty amazing. You make it vibrate. The method is just brilliantly simple in theory. First, you take a small, simple beam of the composite material and you make it shake. As you change the frequency of that vibration, you listen for its resonance. That's the frequency where it wants to shake like crazy. Think about finding the exact musical note that makes a guitar string really sing out. That's resonance. And then, from that resonance data, you can actually calculate the material's most important mechanical properties. Okay, let's step into the virtual lab and see exactly how this whole thing works. We're going to walk through what's called a flexion or a bending test, step by step. So here's our setup. We've got a rectangular sample of the composite, let's just call it a beam, and it's clamped down securely right in the middle. Then, one end is attached to a mechanical shaker, which is going to provide all the vibration. The shaker then starts doing its thing, sweeping through a whole range of frequencies, from low to high. And the whole time, you've got sensors that are precisely measuring the movement, how much the free end of the beam is wiggling. The goal here is to hunt for those magic frequencies where even a tiny little shake from the machine causes a huge vibration in the beam. And when you plot all that data, the vibration response versus the frequency, you get a graph that looks something like this. And those sharp peaks, that's the evidence we're looking for. That's the gold right there. Each one of those spikes represents a natural resonance frequency of the material, a frequency where that beam just loves to vibrate. And these are the clues to its hidden strength. And as Yvonne Chevalier, the author of the paper we're looking at, puts it, the material's secrets are revealed right here. It's at these specific resonance peaks, or modes, that calculating the fundamental properties of the material becomes, in his words, relatively simple. Okay, so we've got our peaks on a graph, we've found our clues. Now for the really cool part. How do we translate this vibration data into the hard numbers that engineers need to design the next generation of jets and race cars? This table really breaks it down. It's a surprisingly direct translation. The exact frequency where the peak happens, we'll call it Fn, tells you exactly how stiff the material is. So a higher frequency means a stiffer material. And then the width of that peak, let's call that delta Fn, tells us about the material's damping. That's its ability to absorb energy and stop vibrations. Two absolutely critical properties decoded from one simple test. It's amazing. Ultimately, all of this work, the whole shebang, is done to find one key number, the Young's modulus. This is kind of the holy grail of material testing. It's this fundamental measure of stiffness that tells an engineer precisely how a material is going to bend or stretch under a specific load. And with this number, they can design parts that are both ridiculously light and perfectly strong enough for the job. All right, so let's zoom back out. We've been deep in the weeds of the test, but what does all of this mean for the big picture of next-gen manufacturing? So let's do a quick recap. Composite materials are the absolute powerhouses of modern engineering, but their very nature makes them complicated. Their secret weapon, anisotropy, means their strength totally depends on the direction you measure it. To solve this, engineers use these really clever, non-destructive vibration tests. And by finding a material's resonance, the musical notes it likes to sing, they can precisely calculate its stiffness and strength without ever having to break it. So the next time you see a sleek race car or you're getting on a modern airplane, you'll know. You'll know that its incredible strength and safety were checked, not by brute force, but by listening to the tiny, subtle vibrations hidden deep inside its structure. It really makes you think, doesn't it? The materials of tomorrow are built on vibrations we can barely see. What other invisible forces are shaping our future?